All right, everybody. I'm Jake,
I'm Will.
and we did our project on using reinforcement learning to navigate a virtual maze. So, welcome to our amazing project. Um, so, as we kind of mentioned earlier in the previous slide, we did our project on using reinforcement learning to navigate a virtual maze, in which we used a kind of a custom-made environment to traverse a maze, in which Will talk about in a second what exactly we did.
Yeah, so basically, reinforcement learning in the most general sense requires an agent and an environment. And so in our case, our agent was a virtual robot and our environment was a maze. And so our RL algorithms also require a reward system, which basically gives the agent a reward based off of its actions. And in our case, the closer our agent got to the goal, the higher the reward was. And so this is some screenshots of the pre-existing environment we had, which is basically just a maze with these arrows on walls, which basically point the agent in the direction of where the goal state is.
So some of our motivations behind this, and there are a few, which we'll get into right now. One is just our kind of enthusiasm for RL. Will and I are both pretty excited about artificial intelligence, and just kind of having robots be able to think for themselves. And even though RL is kind of one of the lowest states of AI at the moment, it is still kind of like a really cool feature to have a robot think for itself and kind of do problem solving based off the rewards you give it. And so just kind of having this enthusiasm is one of our biggest motivations for diving into this project. Another one of our motivations is the real world applications. And they're starting to become many real world applications. One, for example, one of the biggest is the Mars rover, in which it just needs to kind of navigate. And even though that has sensors, it still kind of is the same same idea as our project. Even though it's a much bigger and wide range project, it's still an agent that's trying to accomplish a goal for some sense, and kind of dodge obstacles and problem solve in that ideal world. And so there are just a bunch of other applications in which RL can be applied and AI can be applied. And so we just kind of very interested in these applications, and that's one of another big motivation we had. So the next step is our approach and the ideas we tried to apply to our project. And the first one was using OpenAI Gym. And so OpenAI Gym is just kind of an open source toolkit in which people are able to train their own reinforcement algorithms or apply it to their own algorithms to their own personal environment. And so there are like hundreds and thousands of already pre-made environments and algorithms in which you can go in and play around with and test. It's kind of a unique tool in which you can kind of use fun things to learn more about reinforcement learning and other types of AI algorithms. And so there are already custom-made environments like Atari or even Doom or Minecraft, in which you can go in and play around with those AI interfaces and really train them to complete missions themselves. And our next step was applying Q-learning. And Q-learning is kind of the most basic form of artificial intelligence in reinforcement learning. It is just the idea of an agent moving and taking a step. And then after it takes a step, it gets into a new state. And in that state, there are a number of rewards and actions it can take. And so Q-learning is essentially just making a large table in which the agent is able to get a positive or negative reward, and it remembers those rewards and stores them in a table. And then when it goes back through, it's able to kind of find the most optimal path to its goal state in which it receives the most reward for getting there. Unfortunately, that didn't work, and so we needed to move to a more complex algorithm. So we used deep Q-learning neural networks along with A2C. And essentially, these both use neural networks in which they're passed in the action and state and then receive the most positive reward. And really, we needed to take a step into this because our environment space was so much more complex than a simple AI example, I guess, or environment example. And so there were so many options that our agent could take and so much space for it to do that a simple Q learning wouldn't work. So we needed to have these neural networks to be able to pass in a number of actions and train it on the number of actions so that we could receive the most optimal reward. And our reward system that we wanted to use was essentially having our agent start at one point, and then the closer that it got to a goal state, it would receive a high reward. And so moving away from the goal state, we receive negative, moving towards, we receive a positive. And this is kind of the most basic form that we could think of, but we still thought that it would be really efficient. And then with that kind of basis of reward system, we wanted to apply different features, like if it was stuck in a wall for a certain amount of time, it would receive a negative reward to try to encourage the agent to go and explore on its own. And so some of our results and discussions. So we used a 404 not found here just because we were never really able to have our agent reach its goal state, which was our overall goal, because we wanted to be able to time the agent to see how long each algorithm took. And then kind of be able to display those results and then play around with other algorithms. But unfortunately, because we didn't have the time and also our unfamiliarity with reinforcement learning and AI, we were not able to do this. But we still were able to get a couple things in which, next slide, we were able to kind of just train our agent and get some feedback on how long that training took to see which algorithm trains faster. And we were also able to see like which algorithm, whether it be DQN or A2C, was able to kind of encourage our agent to go based on our reward system. And so as you can see in this next slide, our inference demo. So the first one is DQN. And it's fairly interesting seeing the agent kind of explore like this. So it starts in its goal state and is able to kind of follow along. And as you can see, it gets stuck in a wall. And this GIF is cut short, but it remains in the wall for the remainder of the epoch. But it's still cool and interesting to be able to see the DQN kind of working in action and telling the agent to go explore. And then the next one is our A2C. And this was a problem that we had with just having it spin around in circles. Each of these were trained on 100,000 time steps. And they still were not able to kind of go explore beyond these GIFs. And so this was the problem we ran into, and Will now explain why we ran into these problems.
Yeah, so we basically like focused on two major areas where we think we ran into trouble with our algorithms. And the first one is the complexity of the maze. Originally, we relied heavily on an example from Simon Thomas's GitHub page where a taxi was navigating a kind of pseudo city and picking up passengers. And we thought that this was a really great example because it was so similar to kind of the problem we were trying to solve. But you know, after trying to implement our learning algorithm, we realized it wasn't working because our set of states was so much more complicated. There was, as Jake was saying earlier, just so many more options and areas to explore than in the taxi cab example. So the complexity of the maze made our algorithm a lot more complicated than we thought it needed to be. Next was our reward system. And Jake just showed the two inference demos of DQN and A2C. And so in A2C, our agent kind of just spun in circles because there wasn't a good reward for moving forward or moving closer to the goal state. So the agent didn't really know what to do besides spin in circles. And then for our DQN implementation, our agent actually did get to explore a little bit, but would get stuck in corners. And this was because it wasn't receiving a positive reward for getting out of the corner. And basically it was already in the position that was giving it a maximum reward. And so it would just stay there. While the direct ethical implications of this project seem to be pretty minimal, it seems to be pretty harmless, I think it's valuable to talk about kind of the more overarching ethical implementations of the proliferation of robots in general. The example here on the left is Uber Eats robots delivering food instead of people. And there are a lot of studies that have been done about kind of projections for how many jobs will be replaced by robots in the near future. And while there are other studies that say, even if that happens, there's going to be a larger creation of jobs and it actually will end up increasing the overall amount of jobs. It's important to note the impact this could have on the way society operates. And I think it's important to think about the overall ethical implications of any computer science, especially AI related project. So in conclusion, although we did not get our agent to successfully solve the maze, Jake and I both feel like we learned a lot about different RL algorithms, and we just think that this is a field that, well, first of all, we didn't have a lot of knowledge in, but also that's just really important, rapidly growing, and is likely going to play a big part in our generation.
And so thank you for listening.